let's start. In these, I think there are 13 or 14 of these so far, based in, and that today we're going to consolidate some things and explore the solar spectrum. What this is going to be is it's going to be the way I think. I'm going to give you a summary of how I think about when I look at a spectrum. How am I going to go about understanding? Now I know it's the sun that I'm looking at, right? So if you gave me this spectrum, I would pretty soon tell you it was a G-type star because I have that experience. Now I understand that most people probably don't have that experience, but so I'm gonna cheat a little bit because I know what the sun is. I know what the abundances of the elements are in the sun pretty well. I know the state of the atmosphere already pretty well. So, but what I'm going to do is I'm going to try and go through and explain to you how I use basic physics to understand, you know, the nature of the spectrum that we see, and just go from there. But I'm going to have to assume, you know, we're sitting next to a star. We've got, you know, 6,000 Kelvin. It's a density of whatever it is at the surface. It's got so those things are kind of going to be implicit. So if there's some assumption you think I'm making, you can stop me. But I'm going to go through and explain from radio all the way down to X-rays, and we're actually going to go in a complete circle, all the way through the atmosphere of the sun. I'm not talking about spectroscopy in terms of what's in the interior, the photons that we can't see. I'm just going to talk about from the atmosphere. That's the place where the photons escape. So this is a nice log-log plot. There aren't many log-log plots that make a lot of sense to me in this business, in the solar spectrum. If you type in solar spectrum, it's quite hard to find this. And all it is it goes from on the left-hand side, so it's basically frequency increasing as you go towards the right. So it's energy increasing towards the right at the top there. Okay. So, but this is a representation of what the solar spectrum looks like in terms of what's called the brightness temperature. So if the radiation were radiating at that wavelength, and so this is a very smooth version of the sun, and those dashes on there are not just dashes. Those are absorption lines here. Where are we? You can see absorption lines in here, and you can see emission lines in here. They're a little bit. This is a hand-drawn picture by Gene Everett, I think, who's recently passed away. He was trying to do fundamental work on the sun's atmosphere and develop these real cornerstone models in one dimension, stratified models of the atmosphere. So what can we see here? We can see that at radio wavelengths, this is actually microwaves, 1 centimeter. It sort of continues up, and we have a hot. So this is a representation of the sun's spectrum. This is the spectrum. It's just written down in terms of an effective temperature of radiation. So there's a one-to-one correspondence between intensity or brightness and the Planck function, which is at a given wavelength, which we know on the x-axis, and now we can just solve for the temperature and say, this is what it is. So this is a spectrum. This is the spectrum, just represented slightly differently. And you can see it's very hot up here. We know that the surface temperature is somewhere down in here. And then, so we're looking here, and we see that what's happening is that we're looking at the chromosphere, and then we're looking at the photosphere. Again, this is jargon I'm using from solar physics. Basically, not so deep down, so we've got quite a bit of opacity here. This is sources of opacity, okay? And what that means is the inverse of the mean free path of the photons. So a very large number here means the photons don't get very far. So that means we can't see very far in. So we've got this hottish sort of chromospheric brightness going on. And if we were to measure this, and this has come from measurements, and you can go into literature and find them, even down to 100 microns, 10 microns. Now there's a bunch of water vapor absorption. There's absorption up here from other reasons, etc. But what we see is gradually see the presence of increasing absorption lines here. This is represented by this, which switches over to emission lines around here. Okay, and you can see the temperatures going up and up and up. And eventually, if you were to expand this graph, which I would like to have done, but I didn't have the time, I would say the corona is outside of this as well. So we start from the corona at very long wavelengths, and then we go all the way back to the corona at very short wavelengths, which is kind of ironic, really. But there's a good physical reason for that. It's to do with the lessons that we taught early on in the spring here. Okay, so forget the lower panel. So I'm going to go from radio all the way to X-rays. So Hanley might be able to tell us why I've restricted radio wavelengths to those which are shorter than 300 meters.
Why? I don't know.
Because radio waves don't penetrate the ionosphere in the daytime, so you can't look at the sun.
I see.
Okay.
So they do, if you measure like 600 kilometers or something.
Yeah, but you don't have big radio telescopes at 600 kilometers.
Oh, okay.
Not usually.
No, not really.
Okay. But this is the kind of question I'm going to be prompting you with. So what are the main considerations that I would think are important to understand? We'll see some plots of the sun spectrum in a minute, but first of all, atmospheric transmission. Let's pretend we're 70 years ago, before the space age, and what can we see on the sun? Well, that still remains the best studied part of the spectrum, right? With some exceptions. People have gone overboard with the UV and measured lots and lots of things in the vacuum UV for which you need to be above the heights you were talking about. So we know the UV pretty well, so first of all, we're going to look at the atmospheric transmission from the ground because it's a practical issue. And then the main emitters and absorbers. Okay, we understood from the lectures we had so far, or the tutorials, that there's an emission and there's an absorption of photons we've got this system which I think we need to treat as a plasma, which is treated classically. We're not dealing with quantum mechanics, it's a very dilute thing, so we're not dealing with white dwarf atmospheres or something. This is just classical motions of electrons. They're represented by plane waves in quantum mechanics, or just by paths in classical mechanics. And we've got this radiation field, okay? And the plasma consists of just charges, but also we've got three pools of energy. We've got radiation, we've got the separated charges, but we've also got internal degrees of freedom within the ions and atoms that also contain energy. And and the whole business of understanding spectroscopy is understanding how these are coupled. Okay, what we want to know is about the plasma. That's the goal, right? We want to know what the magnetic field is. We want to know what the densities and temperatures. We want to know if the distribution functions are Maxwellian. We want to know all this stuff. Okay, so we better understand. The coupling between the radiation and the plasma and the internal degrees of freedom. The internal degrees of freedom are really important because they're the ones with the long-lived eigenstates that have very sharp transitions between them, and that's the diagnostic tool that's most powerful for us in looking at the universe around us. It's a matter of some luck that the fine structure constant, the various combinations of elementary quantum and electrodynamic constants are such that we get very narrow lines. Narrow in the sense that they're small, they're natural line width, they're almost like delta functions. So we can use them to map out the speeds at which things are going. We can use them also to split them with fields. We can and try to find out about the fields. So I'm just saying a general introduction here, but basically this is the main considerations that I would need if I wanted to figure out, say, a spectrum of a star or a quasar at the other end of the galaxy. What are the main emitters and the absorbers? How is the radiation coupled to those main emitters and absorbers, those being interactions with the plasma and the internal degrees of freedom? Well, we have lots of free electrons around, right? And we know that radiation comes from acceleration of charges, so that's what we've got. Acceleration of charges occurs in these bound states, these internal degrees of freedom. Those are the spectral lines, and we get those all the way from X-ray to infrared wavelengths. And we better understand what the typical particle energies are in various plasmas, because if we have a very low energy thing like this atmosphere, we know we've got neutrals, right? And we've got molecules. It's dense enough even to form molecules. The sun's atmosphere can do that a little bit as well. So we need to know the state of the plasma, and that's dependent on the amount of energy per particle, which is nothing other than temperature, and also the density, which is to do with the way the object has gravitationally collapsed. What I wanted to talk about, and won't have time today because I started writing this is what we get when we look onto the disk of the sun and then block it with an eclipse, or just point off and assume there's not much scattering on what's going on above the limb. Basically, that's just setting the lower boundary for the radiation to effectively zero. And that changes a lot of stuff. So you can see, for instance, magnetic dipole lines in the corona, which you can't see on the disk because it's a million times brighter. So you need 10 to the 12 photons to get a signal-to noise of 1. I mean, that's difficult with detectors that have 64,000 well deaths. Okay, so here's the first thing: the transmission in the daytime. So we're blocked off at short and long wavelength ends due to the plasma frequency of the ionosphere, and all that means on the long wavelength end is if you have a slow enough variation, the natural frequency of oscillation is if that is higher than this, then the electrons can freely move without any effect from, or not freely, but they can move within the context of, say, a dielectric kind of calculation. So the electrons are going to respond to this low frequency wave, and they're going to radiate, and that means that you're going to get reflection off the ionosphere. So the radio waves come in and they go away again. Okay, classical picture. We also have water vapor absorption at long wavelengths down here. So, if you're in the top of the mountain in Hawaii, you're going to see a different thing from, downtown Seattle or something. I mean, you're not going to see anything through the rain up there. But this just shows you roughly what visible light is here. The ultraviolet cutoff is down here. This lower dark colored thing is where the cutoff is. That's 3100 angstrom, 310 angstrom, and that's due to ozone. So that's what we're dealing with. We have to look through this garbage whether we like it or not. But now we have the spacecraft that can get above this stuff. Still not straightforward. Even at 600 kilometers, if I put a spacecraft up there and look at the sun saying Lyman alpha, that's not easy to do, because even the Earth itself is surrounded by an exosphere with hydrogen atoms and protons in it. Some of them recombine and emit Lyman alpha, so you've got this mess to go through as well. So it's rather wavelength dependent. Okay, let's move on. So here's the actual visible part, and the infrared part of the solar spectrum, and there you see, for better or worse, the nature of the spectrum. On the right-hand side, it's almost featureless. That's because, because there aren't actually that many really opaque absorbers in the sun's atmosphere that would correspond to transitions at those wavelengths. Why is that? Well, we'll find out shortly. Then we have these much stronger things here. Okay, so these look like small things, tips on the thing, but if you blow it up in wavelength, you'll see that things like this is H alpha, Balmer alpha. We've got things like calcium H and K. These are wicked strong things, strong enough that Fraunhofer could see him in 18 whatever it was with his visual spectroscope, right? And if you've ever seen a spectrum of the sun with a modest resolution, you can see these bands clearly. I mean, you can see the dark lines in the spectrum, A through M or whatever it is that he classified them. So these are the strongest lines. Now, I'm identifying one or two things here. We've got a lot of iron 1, we've got hydrogen, okay, we've got X-rays, we've got UV, we've got infrared, calcium H and K, infrared triplet. Okay, this is, what am I talking about? There's not a lot of calcium in the sun, right? Why are those so strong? Well, we'll get there shortly, and these classes should have given you a hint on that. Should have, and if they haven't, then that's my fault, because I tend to assume some things. But the other thing is, you can see it's very smooth and like a black body spectrum with little nips in it, till we start to get to this garbage in the visible region. And almost everything we know about the sun until, fairly recently, the last 40, 50, 60 years, was based upon this. No idea what was going on here, none here. We knew about there being UV emission on the sun because already, well before we observed it, because we knew we had an ionosphere. It couldn't come from anywhere else. And the ionosphere was vary daily. So that was the first evidence. And in fact, it's like the ionosphere is a detector of UV. The Earth's atmosphere is a detector of UV radiation from the sun. And you can invert it to estimate how much UV flux there must be from the sun, just with a simple model of the ionosphere. You're going to get the answer wrong quantitatively, but you're going to see the solar cycle. You're going to see daily variations. You're going to see sunspots come and go. I mean, it's all there. It's the same thing. It's Einstein's photoelectric effect. That's all it is. Okay.
So the ozone was the ozone absorption was that realized before or after the?
I don't know about the history of ozone too much. Does anybody? I know it's not very healthy to have it at a traffic light while you're waiting to cross the road, right?
But you mentioned that they know that UV from ionosphere is just the ozone absorption. When was that? No, discovered.
I don't remember. I'm sure I read it, but come on, I'm 64.
Oh, Google.
Yeah. Yeah, why don't somebody Google it while we're here and find out before the end of the, you want to try that? I mean, okay. You're welcome to not as well. Okay, so the other thing I would want to know about, so we know about what's going to reach the ground and what isn't. You can just look up with a pair of eyes and see if your eyes are infrared and X-ray sensitive, you could do that. The other thing that we do know about since 1929 with Celia Payne-Koposchkin, the most one of the most underestimated women in the history of science, she figured out that almost everything in the sun was hydrogen. And there it is. This is the logarithm of the number of particles from in normalized, so that hydrogen is 12 in, say, just a piece of 1 meter cubed of the sun. And you see hydrogen and helium at the top there, and there's almost no lithium. So that's the Big Bang done right there, apparently. Right? That's a result of the Big Bang. The reason there's not very much lithium is that there are nuclear reactions that tend to destroy it in the interior, even if for certain kinds of stars. And lithium and boron are just not natural products of what powers main sequence stars like the sun. So, for instance, if I take hydrogen with a number density of 12 in the interior of the sun, and I allow the gravity to pull it together, it fuses. It fuses, but it makes carbon, nitrogen, and oxygen, which is why those are big there. See those three? Okay. And then, so we come along the periodic table, and here we're about a third of the way down, and pretty much anything below here is going to be quite difficult to see because there's just not enough stuff blocking the light. So a line of zirconium or barium, you can find them, and you can get really strong lines because we know that certain levels like to take light out. They have a very strong cross section for absorption or scattering, and so they will pull out a little bit of the light. So you can see lines of barium, things like this here, but you don't really have to worry about them in terms of diagnostic of the plasma. If you're worried about nucleosynthesis and how the hell you make barium, then you better measure it, right? I mean, you know, so what I'm saying is we needn't worry too much about this here, and there'll now be another plot coming up soon. We then need to worry, given that the abundances, this is just the number of nuclei of these things. We don't know anything about how many electrons attached to each one or otherwise. If we're not worried about the spectrum formation, we have to worry about processes which are of the kind that are listed there. So this is the bit where the plasma, denoted by the electrons on the left, and the radiation denoted by the little wiggly lines, determine the state of the internal degrees of freedom of these atoms, like hydrogen, helium, carbon, nitrogen, oxygen, everything, right? So we need to know the probabilities, the quantum probabilities of, say, the first thing happening where you have 1 electron going in and 2 coming out. And then the reverse process is 2 electrons coming in and 1 going out. And then down here, we have the interaction of photons at the bottom here. And so we better know about these things as well, right? So the speed of the electron is obviously important, because if I have enough energy to knock those electrons, pull them out of that well, the well of electrostatic interactions plus the other ones, and I can ionize it to make 2 electrons go off from 1 electron coming in. If that's not moving fast enough, it's not going to get to the threshold, and you're not going to get an extra electron. So we better understand something when we're looking at the spectrum of an object, like the photosphere of the sun, the corona of the sun, a planetary nebula, the broad line region of an active galactic nucleus. We better have some idea as to what's going on in the ambient arena in which these atoms are embedded. And that's described by the electron distribution function and by the photon distribution function, which is nothing other than the intensity of the radiation. There's another thing which determines whether whether these things are going to happen or not, and that's the ionization potential. How much energy does it take to knock an electron off? So we're observing things like carbon, nitrogen, oxygen, helium, hydrogen. We're not observing these guys, they're too weak. We can see even things like this, no problem at all. We have a lot of things in the iron group. Remember I showed you that plot at the beginning with lots of iron in the visible region. It's by far the most dominant contributor to the line spectrum of the sun. But this tells you, for instance, helium is incredibly hard to ionize. Neon is. Well, we know all about that from our physics undergraduate days. These are noble gases, they don't interact. You can inhale that, and barring diffusion across your bloodstream barriers, you're going to be fine. You're just going to sound like Minnie Mouse, right? That's all that happens. It doesn't chemically interact. That's the same thing here. This is chemistry. Spectroscopy is a simple form of chemistry. And in plasmas, it involves single atoms as opposed to complicated molecules in chemistry, like the kind I have to take every morning and every night for health issues. I mean, God knows what levothyroxine looks like in terms of molecular structure. This is really simple. We got one number that we really, really care about a lot to start with, and that's the first ionization potential. How much does it take to pull one electron off? That's important because it determines whether the atom, like helium, is going to be neutral mostly. And it's not going to feel effects of magnetic or electric fields hardly at all. It's just completely neutral. There's not enough energy to strip the electrons off. Even the thermal energy of collisions with other particles in the plasma around it, there's just not enough to do anything to it. It might shuffle it around in direction and momentum space, and in space and momentum space. But now imagine that there could be a time when all these elements underneath a certain line are in fact ionized, but the other ones aren't. And this is what's going on. So why have I drawn a line here? Well, I'm going to cheat. I'm going to say I know roughly what the density and temperature is in the photosphere of the sun. In fact, people like, after Planck's discovery of the explanation of the Planck function in 1900, he could have told you what the surface temperature of the sun was, 6,000 Kelvin. Couldn't have told you what the density was, so we don't know what the ionization state of the sun would have been, and that probably wasn't figured out. That wasn't figured out until Celia Payne-Koposchkin used the psi equation and some equations for the structure, measuring the mass of the sun and the gravitational constant. All that. It turns out that this is the line roughly where anything above that line is probably going to be mostly neutral through the sun's photosphere, the place where all the photons are streaming out, carrying the bulk of the flux. Anything below that, these are the only ones that are ionized. If I'm in a sunspot umbra, the temperature is even lower, and so I would lower this line. I would lower this horizontal black line even more, and pretty much the only thing that would be ionized would be potassium. Now, this may seem, oh, yeah, of no interest, but if there's so little ionization there in the core of an umbra of a sunspot, the conductivity is so low, there are so few electrons, that the question comes, how strongly is the magnetic field in that umbra connected to the plasma? That's really interesting and important to know, because that's going to determine how much like an ideal fluid it's going to behave, and whether it's going to be things like a dynamo are going to operate. Notably, the iron group is down here. So what I'm telling you is, the bottom line to remember from all this is all these elements are going to be ionized in the photosphere. Okay? And none of these will be. The photosphere is important because it carries 99.999%, radiates 99.99% of the energy. The rest is left over for the chromosphere, and then 1% of that is left for the corona on average. So we've already set the stage. in the lectures, I'm going to put these things together now because I've got the most abundant thing you can imagine is hydrogen. In the photosphere of the sun, one of the problems that was identified in the 30s and wasn't resolved until 1938 or so is they couldn't find enough light to block the sun. We should be seeing much hotter material than we can. And it turned out the thing that was missing, and it makes sense if you think about it like this, is H minus. Now, when I was first introduced to H minus, I thought, well, what the hell are you talking about? There can't be a hydrogen with 2 electrons around it. That doesn't make any damn sense. What are you talking about? There's not enough force to hold the electrons on. Well, it's a balance between 2 electrons interacting via the Coulomb force versus the attraction due to the charge on the hydrogen atom. And there is one bound state that this has. This was figured out by people in the 1930s. And it occurs because electrons are fermions and they like to be together. And if I bring a 1s electron, meaning it's at the bottom of the well, and I add another one, so I imagine having a hydrogen atom, an electron comes along and then the hydrogen can capture it, but it can only do it if the spins are opposite, because you have to have an antisymmetric wave function. The symmetry of the wave function is related to the, and you can have exactly 1 fermion per state, but that state is now determined to be not just angular momentum of the orbit, 1s electron. That means 0 angular momentum, L is 0, N is 1 in the bottom of the hydrogen well. But we then have a choice of spins. So our space, our Hilbert space in which the quantum mechanics works, consists of an infinite number of dimensions in space. So we have, 3 dimensions in space. So we've got X, Y, and Z, and we've got to specify the wave function of this one. But we also have to specify whether the spin is up or the spin is down. And this is correlated with the fact that you have symmetry or anti-symmetry. It's a fermion, so there is exactly one state, okay? Now, again, why should we worry about this? Well, there wasn't enough opacity around, and nobody could think, we can't photoionize anything. Ionization potentials are too high. All those ionization potentials, this corresponds to about an energy something like, let's see, iron is about 8 eV, so this is about 4 eV. 4 eV is 10 times the energy of the radiation, at least, well, about that. There's an ambient in the atmosphere of the sun. Okay, there are not enough photons there. There are not enough electrons there to produce. So I've got it slightly wrong there. What I should say is, if you want to block the light, you would think that the light photons coming along is going to get absorbed by the photoelectric effect and knock an electron off. Right? That's Einstein's photoelectric effect. But that only happens at way too short energies in the UV. There's not enough blocking of the light going on from any source. So in a way, this is kind of natural, just from the elementary physics. When I first saw H minus, I thought, this is just insane. What are these people talking about? And, but then I realized, a little bit of thought, you actually, do get this. Now, the next excited state, the next one up, is actually unbound. You can do the quantum calculation simply enough. So you put n equals 2 in, and then you find out that this thing lies in a continuum, which means that it's never going to get. It's not a local wave function. There's not enough pull to keep those two together. If the spins are if you've got an n equals 2 electron, it's excited. This is like a helium. 1s 2s is the first excited state of helium. That's a hell of a long way up in energy, right? So energetically, this does make a lot of sense. So let's move here, and we can see here that the spectrum, at least, and now we're getting to the point where I'm describing where the continuum of the spectrum in the historically not understood part of the spectrum was. There simply wasn't enough opacity in this region here. Okay, so there it is. So here is the energy going left now, This is very high energies. So here are the photoionization edges. So this is, if I have a photon at this energy, it can ionize, it can knock electrons off all of these things and absorb it. But now if I'm at this energy, the only thing left to absorb it is the H minus bound free and H minus free free. Okay. And there's a minimum where these two processes occur. And this is the point where we see deepest into the sun. There's no opacity there. It's the lowest. This is the opacity on the left-hand side. Think of that as 1 over the mean free path of the photon. So if that's a low level, that means the photons have an enormous mean free path. Therefore, we're seeing way the hell down into the atmosphere. Okay. And then at the top, you can see the, and there are the references there. Harry Massey was famous, and his history continued all the way to this present day at University College London. Wilt is famous German. So what's going on here? Let's have another quick look. We're still looking at the nuts and bolts of this stuff. So what is this? These little ticks look kind of strange, but what they are is actually, it's the abundance of the element times the photoionization cross-section. And at low energies, the only thing that we can really say is going to block the light is photoionization of H minus. So that's why this box has been translated over here. So this is where most of the light blocking is going on. I haven't put this on the proper scale, but you can see it's pretty low compared with, say, magnesium. So magnesium is here. So this appears to be about 2 orders of magnitude down from there, which looks about right. So it's not far off. So if I were to put in this cross section for all these processes in H minus, suddenly we understand the spectrum of the continuum of the sun. And as we go towards ultraviolet, remember this is now, so the atmospheric cutoff is about here, somewhere in here. So you can see that photoionization is really going on only below the atmospheric cutoff, right? Okay, so this is why helium, like hydrogen, if I were to plot the Planck function here, it's going to have a huge peak here. It's going to have almost nothing over here. So this is why this is so important. So the spectrum of the continuum of the sun. Now we can look at things like the periodic table. Why is this important? Well, we know that we have, and this actually is from the book. There's a little program you can run to build your own periodic table, and this just came out. My annotations, but anyway. This tells you the configurations of the electrons. So this tells us what the outermost electrons have around them. And this tells us something about the energy level structure of each atom. And this is going to translate into a spectrum of the sun. So again, here's the ionization potentials. This is blocking the light. And now enough of the nuts and bolts. So now we're going to look at the sun at different wavelengths. Okay. Okay, it's not a spectrum. And this is the modern way of doing things. You don't really look at spectra. I mean, they're of no interest, right? I mean, no, actually, there are special missions that get a lot of stuff. But here we go. This is an active sun. There's a sunspot here, okay, just in the middle of the visible light. So this is what people have been looking at for decades. This is the stuff that people didn't get to until the 1950s, the radio wavelengths. Infrared, a little bit of infrared. Then later on in the 1980s, a lot of infrared because the detectors were released by the military, and we could suddenly see all these nice, infrared features. So this is just one wavelength or one slightly narrow filter wavelength. And we can see all these structures, and people get excited about these things and what have you. And but there's so we have some idea of what we're sort of looking at if we had eyes that were monochromatic. You could see through these wavelengths. So I'm just going to play a game here. This is actually an intensity image, even though it looks like a magnetogram. And you can see that the poles are very bright, exactly where the coronal holes are. And we're going to, I know the answer to this, obviously, but what could possibly be that left panel? It's not easy to say. If you're experienced in solar physics, somebody might say helium, because for many years, helium-10-830 for some reason showed the presence of a coronal hole. Okay, it's just to prompt you to think. In radio wavelengths, what have we got? We've got the components. Here we've got free emission. We know that because electrons are accelerated by collisions, and when electrons accelerate, they radiate. That leads us for wavelengths above about 1 millimeter, just because the classical coefficients and the quantum modifications of those for the interaction of light with free electrons tells us that, you know, for wavelengths above about 1 millimeter, we are entitled to try and derive just from the brightness or the surface brightness, what the temperature is as a function of height. So this is none other than an application of the Eddington-Barbier relation, which says that when you look down onto a cloud, an atmosphere, whatever it is, you see down to optical depth unity. So that, say at 1 millimeter, you look all the way down to the deep in the solar chromosphere, and you see a certain brightness, which you then say, well, we know the source function has to be the Planck function, because free emission means electrons colliding with each other. And in a plasma that's had time to relax, that means it's the temperature you're looking at. It's just there's no other parameter it could be other than the temperature. The only other parameter left is the number of them that block the light as you're going along. And there comes a point where that number accumulates to 1, and suddenly you see the intensity coming out from the sun, say at 1 millimeter from the temperature minimum region, and you would measure a temperature of, say, 4,000 Kelvin, 5,000. If, however, I go to longer and longer wavelengths, the blocking of the light goes up with lambda squared. So now if I go 10 times longer, I get 100th of the mean free path. Now I see much higher up, but I'm still blocked by free interactions. There's no other feature other than these electrons colliding with each other that can absorb and emit radiation. So now suddenly I'm seeing something 100 times higher up. I'm looking at the top of the chromosphere, maybe, or the middle chromosphere. I go to 10 centimeters, which is where we do a lot of measurements. That's 1,000. That's 1,000,000 times less, more opaque. And if I go from the temperature minimum up by a factor of drop by a factor of 1,000,000 in the opacity, what do? I see the base of the corona, which is exactly what we see. That's what F10.7 does in the absence of other mechanisms. Okay. Now, there is another mechanism called gyroresonance, in which electrons circling around field lines, but thermal electrons, it would be called synchrotron radiation if it were not thermal, but this is just a gyration of electrons radiating. And it turns out that the thing you can diagnose from this is actually the magnetic field, providing it's not blocked by the free emission. That's where the 200 Gauss comes from. And you have also, to get a net signal in polarized light from one minus the other, you have to have a different temperature gradient. And pretty much you have to have lambda less than 10 centimeters here, okay? So what I'm saying is there's two mechanisms in the radio that I'm aware of that really give rise to, and here I'm specifically assuming thermal electrons. In flares, the game's over. If you've got non-thermal particles, you've got all kinds of wonderful stuff that can happen. You can see why, right? I mean, accelerated electrons radiate. Okay, but this can even be extended down into the quiet sun and what have you, with suitable things called, it's just magneto-ionic theory. That's just saying, you know, you've got a plasma and you allow the electrons to move, but you basically assume the ions are stationary, and you can just simply work out what the amount of circular polarization should be if you were to look down on, say, a coronal hole or the quiet sun, and it's sensitive to things at about 10 Gauss. Okay, a curiosity. the thing I showed you here was that the sun is actually quite bright at 1.8 centimeters. And these kind of observations are not made very often. Most radio work is longer wavelengths than that. This is microwaves. And then you have things like Owens Valley Array, you have ALMA, those are shorter wavelengths than this. So, but there's a little sweet spot in there, and it was at Nobuyama Radio Observatory in Japan, which is a pleasure to visit. It's just the most beautiful place in the Alps in Japan. It turns out that it looks like a Christmas pudding to me. I mean, if you block the disk of the sun, it looks like you've got frosting on the top where the coronal hole is, right? And at present we don't have an explanation as to why this is. It's clearly a plasma property of the coronal holes that's not present in the quiet sun. I mean, it is present in the quiet sun in patches of network, but there are equally well dark regions of network and channels of filaments, God knows what else. I mean, this is not a high resolution thing, but statistically, they're very bright. The South Pole on that is really ridiculously bright. It's like at 11,000 Kelvin compared with, say, 6,000 Kelvin if you just interpret it as the brightness temperature. Okay. But anyway, here we're starting to understand the formation in the radio wavelength. This is my point. Right, the radio, I think, is relatively powerful because it has magnetic sensitivity. All these are continuous kind of spectra, even though there's a resonance involved. It's a rather broad resonance because things like dT by dZ can be very messy in the sun, averaging over large areas. So things tend to smooth out and become, they're not sharp lines or anything like that. Let's have a quick look at infrared. I said that the free opacity varies lambda squared. That's what we just talked about. So if we go to a much smaller wavelength, so now we go from, say, a centimeter to a millimeter to sub-millimeter, the free opacity is relatively small, and the chromosphere becomes transparent. So we're able to see all the way down because the mean free path of those photons is getting smaller and smaller. So then we have to imagine what other sources of light blocking there are. And H minus continuous opacity is the next biggest thing that comes in. And then superimposed on the spectrum, which is sort of just, you're looking down to the photosphere where H minus is doing its thing. It's absorbing photons and re-radiating them thermally. There are relatively weak molecular lines. And they're always of the first or second spectra, meaning they're always neutral or singly ionized lines. No third charges at all. And the separation between single and ionized is what I talked about with the ionization potential, that horizontal line. And so the questions then arise, why is it H minus, and why would it be deep photosphere? Well, if you think about it, H minus is a hydrogen atom, and then you have to have a collision with a free electron. This involves it's like H combining with C atom. You got to collide, and you would generate an orbit a potential, and you would glue together lines of CH, which are seen in the sun, the molecule CH. In the same way, you've got to glue on an electron onto hydrogen that has a relatively weak ionization potential for H minus to H. And what you've got to do is you've got to have a lot of particles around to make a lot of H minus. Now, even deep in the atmosphere of the sun, the cross sections and the Saha equation has it has density squared on one side and density on the other. And the number of H minus atoms, is proportional to the number of H times the number of electrons. So it's got to happen deep down. Because if we go up higher in the atmosphere, NH and NE drop like a rock exponentially with height. And so it's got to be deep photosphere. Okay, these are the arguments. I'm just telling you that these are the arguments that from what we talked about in recent months. So what kind of atomic transitions could these be? Remember, this is infrared, so these are very long wavelength. In other words, the energy differences between the atoms are very small between the levels, okay? So this is a spectrum, famous spectrum. You probably know about this stuff, do you? The infrared.
No,
I mean,
unfortunately not.
well, this is an idea of trying to figure out as a function of height. This is altitude of a balloon, okay, in kilometers on the right hand side, and these are the measured spectra. I mean, it's an absolutely beautiful spectra, right? These are like Fourier transform spectra, okay. And basically, what I'm showing you is you can see that all these lines as an altitude get stronger and stronger and stronger until you get almost nothing down here, right? This is presumably 20, I don't know, or 15 kilometers or something. So, you know, you look outside of your aircraft and you can see something like this, nothing in this wavelength band, 15 microns, 14 microns. That's just gone, isn't it? So the solar lines in here, pretty much none of this can possibly be solar because they're still aren't gone, these features, right? So these, even at 80 kilometers, you've got stuff absorbing the light out in the infrared, right? You know, that's really amazing. And this has to be some kind of molecular absorption from the Earth's atmosphere. But the things that remain, this is the sun spectrum here, pretty much. That's it. That's all it is. And so, you know, this is part of the reason why I started at the beginning saying you better understand your so the sun spectrum consists of a continuum and a bunch of little weak lines in the infrared. Okay, this is 15 microns. Let's go to another place and we can see I've marked, this is now 12 microns. And this is the spectrum of the sun. And I've marked with those vertical bars what are most definitely solar lines. I mean, these are for sure, absolutely for sure solar lines. Again, measured, actually, look at this. They're measured from Denver, Colorado. These guys, Mercury's, were at the University of, somewhere in one of the Denver campuses, can't remember which. And they're famous for publishing a nice, beautiful spectrum of the sun in which they removed some features because they thought they were spurious. So you can see you've got nice, strong lines here of, and they're identifiable. These are pretty evenly spaced, right? So it has to be a molecular spectrum, like a vibration, rotation, splitting. So it's the same vibration state, different rotations almost certainly, and the difference in wave numbers is, you know, 2 inverse centimeters. That's a very small energy. That's a rotational energy of some molecule. I don't even know what it is. Okay, but now look, what the hell is this? It's in all 3 spectra. These are taken in Denver. NCAR, Voltec, 1978 at NCAR. These were taken, the bottom one. Okay, so you know, even from Boulder, you can see these things in infrared if you go high enough in a balloon. Okay. So, but this is not spurious, but they took them out of their atlas because they had no explanation for them, right? So we have this continuum, and we have weak lines. The lines are weak. They're very long wavelength transitions, and that means that they must be close together in energy, right? Because you've got one state moving to another eigenstate. These are long-lived states, and that's where these transitions emerge from. So, but they must only come from either single ions or neutrals. And so my argument would be these have to be high up in the term system of atoms. What do I mean by that? I mean, these are not going between the ground level of an atom like Lyman alpha, hydrogen. The 1s to 2p transition is at 1215 angstrom. That's 10 electron volts. This is, you know, at 800 inverse centimeters. That's a 10th or a 20th of an electron volt. So hydrogen, the first jump you can make, it needs 10 electron volts. But these transitions are occurring between things which occur at a hundredth of that or something like that. So the only place those can be in these atoms would be very high up, or they're molecules. That absolutely has to be like that. So that's the kind of argument I would use here. Now, we look at these guys and you go, what the hell is going on? These guys took them out of their publication, you know, and then some people looked again at these things. And in the end, an explanation arose, and this is just a blow up. Again, we're looking at similar, this is like 8 microns, 9 microns, okay? And there's a model and there's a calculation. You can see a beautiful fit. There wasn't anything, but what's going on is you can see this is actually a neutral magnesium. Why magnesium, right? Well, it's one of those ones that lies below the line. That means the bulk of the radiation, the bulk of the material is ionized in magnesium. Okay. That means that the bulk of the population is in magnesium 2, it's magnesium plus, and so magnesium 1 is a minor species, but that's a good thing in one sense. That means that in this plasma, electron comes along, hydrogen comes along, hydrogen doesn't do anything, electron comes along, oh, I'm going to grab that electron, and what's going to happen is I'm going to recombine, and during that recombination, I could recombine to the ground state, n equals 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to whatever you want. Sort of 100 or something is where the cutoff's going to be. But it means that we've got a real reservoir of things at higher energies which can trickle down. And what's going on is they're trickling down, and this is n equals 6. I mean, the ground level of magnesium 2 is an n equals 3s state. It's a sodium-like ion. So n equals 3. This is n equals 6. This is way the hell up in the term diagram. But that's in my way of thinking is perfectly natural, because I've understood that there isn't much neutral magnesium around. And so these lines, whatever's populating these levels, must be coming from magnesium plus, not from the bottom up. It's coming from the top down. And when you come from the top down, things change a bit. And here you see these beautiful absorption lines, and these are low angular momentum states, S to P, these ones on the left, right? But this is a really high angular momentum state, 7H to 6G, and they're in emission. I mean, I think this is a beautiful thing in this part of the spectrum. Emission lines usually mean, oh, it's the corona. Has to be the corona. But this is neutral magnesium. There's no freaking neutral magnesium, not even any magnesium plus. It's all in magnesium 9 electrons ripped off. There's no way in hell that's the corona. Oh, well, then it must be the chromosphere. And Hal Zirin, a famous guy from this institute, wrote in paper saying, oh, it's got to be chromosphere because this looks kind of like calcium lines or something. Well, not calcium, but, you know, we've got some emission, and we know that the source function rises even in the presence of scattering, in the chromosphere, which gets hotter. So an emission line, it must be, it can't just be an absorption line formed like in the photosphere where the temperature gradient is negative. So when we look in the wings, we look deep down where it's bright. We look in the core and we see higher up where it's dim because the temperature gradient, and so you end up with an absorption line. That's the standard explanation of absorption line. This is emission. So what's going on? What's actually going on is very interesting, and it's to do with we know for sure that if it's magnesium 1, it must be formed in the photosphere where the temperature gradient is negative. It's getting so it must, if it's an LTE, it must be an absorption line. It can't be anything else. So therefore, I conclude it's not in LTE. Can't possibly be in LTE. And yet it's formed way the hell deep down where the collisions are really strong. You'd expect LTE to be a pretty good approximation. I mean, what the hell is going on? Well, what's going on is that those n equals 6 and 5, and 5 and 4, and 4 and 3, they're all either getting photoionized again, because it's not much of an energy gap, or the Einstein A coefficient is just spontaneously decaying like a cascade in a waterfall down to the ground state. So if you look at the actual dynamics of population in these things, and that's what these detailed calculations did, you find that the transitions underneath these high-lying n equals 6 levels are starting to escape into space, deep down. So what that's doing is it's draining the population. So say I have a 5-to-4 transition, right? Hydrogen, that would be in the Wundt series or something like Balmer alpha, right? Something like that. That's 3-to-2. We go to we just have, it's just one of these high-lying levels that comes down. If I start losing radiation in Balmer alpha, that means that the population of the n=4 level, n=3 level is dropping a lot, right? So what's going on is these levels are kind of, photons are going out, and the inner degrees of freedom are such that the number of the population density of the lower levels are starting to drop. That's starting to sound like a population inversion. I mean, do you remember having classes in lasers? So a laser, what's a population inversion? It just means that you've got a thermal situation. You've got this box of helium and neon. You warm it up, and then you put some reflectors on either side, and you do something to the helium to excite the levels, and they sit out there for a long time, and then they bash into neon, and they end up with a higher excitation of neon. So you end up with more population in neon than you really wanted, as a result of collisions with helium that you've artificially put into your thing. And then you make the radiation go like this, so you increase your path length. To get a laser, you need a population and a very long path length, right? This is not a laser, but it's on the way. It doesn't have enough path length. There's no, and so what I'm saying is, if you think of it mathematically, the opacity goes like e to the minus tau, and population inversion is going to give you an e to the plus tau. That's a pretty nice thing, right? Normally, you remove those solutions from redshift transfer because you say, you know, at infinity, I want the thing to go, the optical depth to, I want the intensities to go to 0. So I don't allow any solutions to the radiation field that look like e to the plus tau. But here, we've got a situation where we've got a population inversion, and there are such things as masers and even lasers in astrophysics. And so what do you need to do that? It's redshift transfer. It's that simple. What's happening here is you're sort of sucking out the lower level population as opposed to pumping up the upper level population to generate an inverse, so you get a plus tau, and you get a little bit of a magnification of the radiation field, but you don't have the huge path lengths you need. But masers do occur, and in fact, my first subject when I was 21 as a graduate student was to look at how to make masers around lake-type giant supergiant stars. And there, supergiant star, I mean, that's the size of the orbit of Mercury, of Jupiter or something, right? So you have an enormous path length, right? So a tiny inversion, how do we get an inversion? Well, it has to be non-LTE. That means that if the star is hotter and irradiates a certain molecule, you've got a characteristic temperature of radiation exciting this plasma here at a temperature, say, 3000 Kelvin, where the actual temperature of the gas locally is maybe 500 Kelvin. So you've got the conditions you need. You've got a high energy source like the helium would and the neon laser. You've got this high energy system, but it's just redshift transfer from the stellar surface. And so when you look at maps of the sky around these stars, they observe with very long baseline interferometry, and you see these little hot spots. Those are all masers radiating like crazy. And so I'm going to have to stop there because it's 5. So we've got as far as the infrared. We haven't got as far as the the main part of the spectrum. But what I've done is, what I hope I've shown you is that the way I think about explaining various kinds of features that we see in the solar spectrum, it's a cheat because it's all known, right? But I'm trying to say, if I were to now say, if somebody would show me something from a, you know, an O star or a carbon star or something and show me some data, this is the kind of arguments I go through to figure out how to understand the spectrum. And I think I personally find a lot of pleasure in trying to diagnose that kind of thing. And you know, if you send me a spectrum and don't tell me what it is, I can I can probably narrow it down to a few objects that it might correspond to. Of course, if you send me a lab spectrum of a red shirt, I don't know what I would do with that because I don't understand. It's too complicated. A red shirt has got biological molecules in it, right? I mean, it's a complicated thing. But the simple plasma stuff, it is simple and it's understandable from basic physics. That's the only point I'm trying to make. So next week, I probably ought to, let's see how far we got. Yeah, not very far. So next week we'll continue and we'll go all the way into the UV and the X-rays where it gets complicated but simple again. But this whole thing, it's not as complicated. There's too much jargon in astrophysics. There's too much jargon in solar physics. It all comes down to nuts and bolts of how atoms interact, their internal degrees of freedom, and these three places where you've got energy: internal degrees of freedom of the atoms, external plasma energy, and the radiation field. And the radiation field is non-local. So that's pretty much it today. My goodness, we have Herr Knölke here as well. Guten Morgen, Herr Professor Doctor.
That's correct. I'll actually be in shortly.
Oh, nice. I'll be in my office.
All right then. See you then. Thanks for your lecture.
Yeah.
Okay, I'll get ready.
Okay. Any questions, anybody?
Yeah, I have a question. So at the very beginning, you were showing the temperature, right? The temperature of the radio wave are actually pretty high, but their intensity is very low.
Yeah.
And I was just wondering, the absorbed part by the ionosphere, how big of a heating source that is?
Probably nothing.
It's so tiny, right? So.
Well, I'll tell you how I figured that out, right? It comes basically from either the chromosphere or the corona. The total amount of energy, the flux of energy coming into those regions minus the flux of energy coming out is 10 to the minus 5 of the solar luminosity at most.
Oh.
So any radiation coming from this thing, that's an upper bound on the radiation. It's really easy to understand these things if and I think I got this from my PhD advisor, but I got it more from a guy that was one of my tutors called Dirk ter Haar. I remember he asked me to write, this is an undergraduate, write some essays for me in my second year. So he said, okay, here's the subjects. One's making MRIs or something. Another one was lasers. So I wrote this essay on lasers. So he looked at the laser, like, 30 pages thick and handwritten and hand-drawn figures. And I gave it to him. So he looked at it and put it aside. And then he got a piece of computer paper out and wrote down Schrodinger's equation. and then went from there to describe how lasers work. I mean, that's the kind of person I've tried to become and never achieved it. But, I think I have sorted through a subject, plasmas are classical, radiation field can be treated as classical, but the internal degrees of freedom is all quantum. And it's that interaction between those things. That's the book I'm writing at the moment on how to, and it's supposed to be short so that someone like you guys could, if you said, oh God, this person referenced, hyperfine structure in his talk today, I'm not interested in that. You could just go to this book and say, what the hell is that? And you go, oh, okay. Yeah. And why is that present in chlorine but not in carbon? Why is there no? Oh, it's because the isotopes aren't stable. That's because there's an odd number of isotopes versus even, and then you can figure out why it would be important way to use it, stuff like that. But it's all in the physics of everything. I mean, I like, my favorite book to use is Layton 1959, which is just an advanced undergraduate book on modern physics, and it's got everything in there that I still don't understand all of it, but it's the physics is all done at that point pretty much. The rest is details, The only thing I think is different now is the idea of entanglement, which has got a lot of emphasis, and things like the Hanley effect. That's an effect of entanglement, that we're using to try and diagnose the sun. I mean, the problem with entanglement is the moment you touch it, it all disappears. It's like, there's a kid's story, right? Where there's a character surely there's a character in a nursery rhyme or something where you've got, I'm thinking of something, what is it? It's, well, you've got this wonderful thing, but the moment you try to embrace it, it just goes poof, I think nursery rhymes and children's stories, some of them are really violent. I mean, it's designed to make you could scare your kids to death in principle, but we all grew up with them, right? They were always ogres.
The green brother, what do you call that?
Yeah,
Yeah, it was a German, right? Yeah, that's it. Those stories, some of them are scary.
Oh yeah, Norwegian. Have you read any Norwegian folk tales? Oh my god.
No.
It's scary stuff. I'm going to stop the recording before we go on the record as being complete idiots.
So did you find the ozone? Did you look up for ozone discovery or the absorption? Oh, okay. That's it.
So Berkey, Ben, how are you doing?
Well, pretty good. Mostly following.
Are you doing well in Hawaii at the moment? Are you getting any closer to actually operations or anything?
If one assumes that we will get back to operations, every day is one day closer to that date.
Good.
I think we're 2 permits away from